A warm welcome to the 11th lecture on the subject of wavelets and multirate digital signal processing, in which we proceed further on the theme of the two-channel filter bank. You will recall that in the previous lecture, the 10th lecture, we had looked at what happens when a sequence crosses a downsampler and an upsampler. I would like to put before you the effect in the Z domain once again when we cross a downsampler and when we cross an upsampler. So, today's lecture, as I said, is entitled the two-channel filter bank. And we intend in this lecture to talk about this structure, which we have been repeating often again. But today we intend to analyze it threadbare, so to speak. Now, remember that H0 was a low pass filter, H1 a high pass filter. You know, it is helpful to get this structure firmly embedded in our consciousness. It is a structure often used in the implementation of a discrete wavelet transform, for example, of the Haar multi-resolution analysis. So, it does no harm to repeat the structure more than once. We have been looking at the structure almost in every one of the last 2 to 3 lectures, but no harm done. Anyway, here is the structure once again. And what we intend to do finally today in this structure is to relate the Z transforms at every point in this structure. Let us start doing that, and to do that, let us first recall what happens when we go past a downsampler and an upsampler. So, as I said, let us look at the upsampler first, a recall from the previous lecture. Noted from the previous lecture that if you have x in n going to an upsampler by a factor of 2 to produce x out n here, then x out z in this case, maybe to be specific we could say x out u to denote upsampling here. So, x out u z is x in z squared in this case. Let us similarly see what happens when we go past a downsampler. So, for the downsampler by a factor of 2, remember, we had analyzed in detail the case of a downsampling by factor of 2. We had indicated how to generalize, but it was a little more complicated. So, here we have x out d n, if you please. And in fact, we had noted that this operation of downsampling by 2 was equivalent to 2 operations, and let me spell out those operations once again, following which I shall write down the Z transform here. So, we had agreed that this operation of downsampling by 2 can be split into modulation with half 1 raised to the power of n plus minus 1 raised to the power of n first, followed by inverse upsampling by 2, inverse, you know. We had noted that upsampling by 2 or upsampling by any integer factor for that matter was an invertible operation. And in fact, this is also evident in the Z domain. And therefore, we can talk about the inverse here. Now, based on this, we had written down the Z transform. So, we had said x out dz here is half x in z raised to the half plus x in minus z raised to the half. We had derived this towards the end of the previous lecture. And of course, if you did not wish to go beyond the inverse upsampler at this point, instead of z raised to the power half, you would simply have z. So much so then for the z domain effect of downsampling and upsampling. Now, what do we intend to do next? We intend to use these relationships to build up the relation between the Z transform of the output and the Z transform of the input. So, essentially we wish to establish the input output relationship in this 2 band or 2 channel filter bank in the Z domain. Now, of course, I must make a remark here before we embark upon this activity. We are assuming that the Z transforms exist at all points. There are rare situations, or maybe not so rare, where that may not be true. But for the moment, we shall ignore those situations. They are not very frequent in practical applications, and therefore, we can comfortably begin with the assumption that the Z transforms exist at all points. Of course, I do not mean the Fourier transforms exist, they may or may not. Anyway, coming back then to that 2 channel filter bank that we began with earlier on in this lecture, I put it back before you here. I intend now to relate y z and x z in this diagram. And towards that objective, let us number the Z transforms at different points. In fact, let us give the sequences names. So, let us call this y 1, let us call this y 2 and so on. And the very output we shall just call y without any subscript. So, accordingly this becomes y 3, this y 4, this y 5, y 6, y 7, y 8 and then of course y 9 is simply y. So, with this then, let me write down the expressions for each of these. So, let us begin with y 1. Y 1 is easy and so is y 2. In fact, if we look at the Z domain relationships, y 1 z is simply x z times h 0 z. And similarly, y 2 z is simply x z times h 1 z. When we filter with a filter of system function h 0 z, the effect is to multiply the Z transform of the input by the system function of the filter to produce the Z transform of the output. And therefore, y1z and y2z are easy. y1z is h0z xz, y2z is h1z xz. Now, we have before us the relationship that emerges between y3 and y1, and similarly between y4 and y2. As I said, downsampling by 2 is equivalent to a modulation and then an inverse upsampling by 2. So, it is easy then to jump from y1 to y5 first and y2 to y6, because if you think of this downsampling by 2 operation as a modulation followed by an inverse upsample by 2, the inverse upsample by 2 cancels with this upsample by 2, leaving only the modulation here. So, this is a strategy which we might find useful in some circumstances in analyzing multirate systems, particularly when you have a downsampler followed by an upsampler. If you have a downsampler followed by an upsampler of the same factor, it is sometimes easier to go past both of them and then jump back behind the upsampler. We will do exactly that here. So, we will put the relation between y1 and y5, and y1 to y5 is essentially just a modulation. Modulation by 1 raised to the power of n plus minus 1 raised to the power of n multiplied by half, and therefore, the Z transforms are easily related. y5 of Z is half y1 Z plus y1 minus Z. And there is a very similar relationship between y2 and y6. Put this back. y2 and y6 are related by the same modulation. Let us write that down too. So, we have y2 is modulated to obtain y6, and therefore, y6z is half y2z plus y2 minus z. In fact, this jumping across the downsampler and the upsampler was useful because it brought us quickly towards the output. Now, we are only almost one step away from the output. That step is also not very difficult to take. We just have two filters followed by a summer, which is easy to do in the Z domain. So, let us complete that exercise. So, now we are here. We know what y5z is, we know what y6z is. y 5 z is acted upon by a filter with system function G 0, and therefore, the z transform at the output here after G 0 is the z transform of y 5 multiplied by G 0. Similarly, the z transform at the output of G 1 is y 6 z multiplied by G 1 z. And in fact, let me take you one step even further. After all, y z is obtained by adding y 7 z and y 8 z, and therefore, we already have y z before us. Let me write down those steps quickly before you now. So, we have y 7 z is y 5 z times G 0 z, and y 8 z is y 6 z times G 1 z, whereupon y z which is y 7 z plus y 8 z becomes, let me put before you the expression for y 5 and y 6 once again. So, let us take y 6 as an example. Now, you are going to involve y 2 z and y 2 minus z. Y 2 z, if you recall, is x z times h 1 z as an example. Now, when you take y 2 of minus z, you would get x of minus z multiplied by h 1 minus z. So, in fact, let me put that down. What I am trying to do is to identify a form of the expression. So, this y 2 of minus z has two terms embedded in it. So, let us focus, let us say for example, on this term here, y 8. So, y 8 z, as I said, is going to be y 6 z times G 1 z. Y 6 z is going to be related to y 2 z. And then y 2 z is further going to be x z times h 1 z, whereupon y 2 minus z is going to be x of minus z times h 1 minus z. What I am trying to bring out from this argument or these equations is that each of these terms is going to have a contribution from x of z and a contribution from x of minus z. Now, later on we shall interpret these terms x of z and x of minus z, but for the time being all that we need to do is to identify that there is an x of z set of terms and x of minus z set of terms, which we can together write down as follows. So, we will say y z in total is of the following form. It is going to have some system function multiplying x of z and some other system function multiplying x of minus z. And using all the equations written so far, we can write down these two system functions, call them tau 0 z and tau 1 z. Indeed, tau 0 z has the following form. It just requires a little bit of algebra to get here. So, I would not actually do all the steps, I am sure all of you can do them. And now, we write tau 1 z as well. So, tau 1 z would be g 0 z h 0 minus z plus g 1 z h 1 minus z. Now, it should be noted that in tau 1 z, which is what multiplies x of minus z, you involve h 0 of minus z and h 1 of minus z. So, you never involve g 0 minus z or g 1 minus z. The z replacement by minus z is only for the analysis side. Anyway, with this little observation, we now write down y z once again for clarity. So, y z is a linear combination in the z domain, of x z and x of minus z. What does this mean? What do you mean linearly combining x z and x of minus z? You see, if the x of minus z term were not to be there, then we have a simple expression there. Y z is some function in z multiplied by x z. That is the good old linear shift invariant system for you with a system function, and in this case, if tau 1 z were to be absent, the system function would be simply tau 0 z. Tau 1 z is the troublemaker here, and we need to understand first what this x of minus z is. What does it do spectrally? What does it do in the time domain? So, let us understand that now. What does x of minus z do? And to answer this question, we put z equal to e raised to the power j omega, as we always do, to interpret things in the frequency domain. Now, when you replace z by minus z, you are replacing e raised to the power j omega by, well, minus z is e raised to the power plus minus j pi times e raised to the power j omega for z equal to e raised to the power j omega. Recall that e raised to the power plus minus j pi is minus 1. So, now we have an interpretation for multiplication by minus 1 in the z domain. Essentially, we are replacing e raised to the power j omega by e raised to the power j omega plus minus pi. In other words, we are shifting on the omega axis by either pi or minus pi. Now, it should be noted that shifting by pi and shifting by minus pi are the same thing. That is because there is periodicity on the small omega or the normalized angular frequency axis, a periodicity with a period of 2 pi. So, there is no problem if we replace plus pi by minus pi there. Shifting by plus pi and shifting by minus pi are the same thing. With that little remark and observation, what we have done in replacing z by minus z as far as the normalized angular frequency is concerned is to shift by pi, whether plus pi or minus pi. And we would best understand what this shift implies if we took an example spectrum. So, let us take an example spectrum to complete this discussion. Let us take this spectrum. Consider an idealized spectrum like this, essentially with lines lying between minus pi by 2 and plus pi by 2 and 0 outside. So, this is the spectrum of some sequence. Let that sequence be x of n. So, this is the normalized angular frequency omega, this is capital X of strictly e raised to the power j omega. But as you know, in discrete time processing, we sometimes abuse notation a little bit and we write just capital X of omega instead of capital X of e raised to the power j omega, which is more correct. But anyway, I must emphasize that as far as we are concerned from the context, capital X of omega and capital X of e raised to the power j omega essentially mean the same thing. Now, with that remark, what happens when you shift by pi here? So, recall that actually this is what x e raised to the power j omega is. So, we will do a bit of zoom here. All right. Periodically repeat it. With a period of 2 pi. This is what x of e raised to the power j omega actually is. So, you can visualize if you shift this either forward or backward by pi, it is going to give you the same thing, and what is going to appear after shifting by pi is the following. Would therefore appear like this. Again, we shall do a bit of zooming here. And so on here. And so on there. So, now your triangles are around pi and then 3 pi and so on, and here around minus pi and then minus 3 pi and so on. So, now again if you take the principal interval which is here, this is what we get. Now, we must be a little more explicit in our relationships here. So, in x of e raised to the power j omega, if you look at the principal interval minus pi to plus pi, we notice there are two segments here for the positive side of the omega axis and the negative side of the omega axis. Let us call the segment for the positive side A and the segment for the negative side A bar, and in fact there is a reason for this. You remember that the discrete time Fourier transform has conjugate symmetry for a real sequence. So, it is with that reminiscence that we are writing A and A bar. I agree that if the sequence is complex, this conjugate symmetry would not be there, but very often we deal with real sequences, and therefore, it is useful to put the symbols A and A bar there just for emphasis. Anyway, now what we will do is, in x of e raised to the power j omega plus minus pi, we shall mark the A's and the A bars carefully. So, here again in the principal interval, this was actually A and this was A bar, is not it? And therefore, this was A and this A bar. And now, what we need to do is to expand the principal interval for our convenience. So, expanding the principal interval, this is what we get. We get an A bar here and we get an A there. Now, just for convenience, I shall show in dotted on the same diagram what we had just for capital X. So, what I am saying is the solid lines here are x omega plus minus pi. And I shall show in dotted x omega, just to be clear. Again, forgive the abuse of notation where we have replaced e raised to the power j omega by just omega for clarity here. All right. So, in x of omega you had a here and a bar there, and now you have a bar here and a there. So, what has happened is in effect these so called negative frequencies between minus pi by 2 and 0 have now appeared between pi by 2 and pi. So, two things have happened. The order of the frequencies has been reversed. So, for example, in principle, a frequency let us say of minus pi by 4 here is more than a frequency of let us say minus, here you would have 0, pi by 8, pi by 4, 3 pi by 8 and so on, and the same on this side. So, if you take a minus pi by 8 frequency here and then a minus pi by 4 frequency there, the minus pi by 4 frequency appears as a smaller frequency here. One can see that, because the order of frequencies from 0 to pi or 0 to minus pi by 2 has been now reordered between pi and pi by 2. So, increasing magnitude of frequency here becomes decreasing magnitude of frequency there. Secondly, the frequencies themselves change. So, actually this is exactly what happens in what is called aliasing. Many of us will recall from the theory of sampling and aliasing. This is something very fundamental. In a course on discrete time signal processing, or in the process of sampling a continuous time signal to get a discrete sequence, these things happen. So, if we do not sample at an adequate rate, we get a problem called aliasing. What is aliasing? Aliasing is a phenomenon where a sine wave assumes a false identity, and there are two things that happen in aliasing. One of them is, of course, that the frequency of the sine wave appears to change. The other is that when you increase the frequency of the sine wave, the apparent sine wave or the sine wave produced by impersonation, if you would like to call it that, seems to have its frequency reducing. So, an increasing frequency, an increasing actual frequency seems to appear as an apparently reducing frequency. These two things together together make up the concept of aliasing, and what we are seeing here is just an instance of aliasing. Why are we seeing aliasing? It is not very difficult to understand. What we have done is to downsample. In the process of downsampling, we have in fact introduced the possibility of aliasing, and this x of minus z term is bringing before you the consequences that would be there if aliasing were allowed to remain. Think about it. X of minus z is therefore called the aliasing term, because it tells you the contribution of possible aliasing. In the 2-band perfect reconstruction filter bank, which we shall soon see, this aliasing should be absent. By perfect reconstruction, I mean if y is to be an exact replica of x, as is the case, for example, in the Haar system, when you have chosen the filters properly. So, you analyze or you decompose, and then you synthesize or reconstruct, and if the reconstruction is perfect, there should be no aliasing. So, this x of minus z term is a troublemaker term in general, troublemaker in this sense. Let us make a note of this. So, the x of minus z term, or equivalently the x of minus e raised to the power j omega, or x e raised to the power j omega plus minus pi term is the consequence of aliasing. What is the consequence of aliasing? We should put it down very clearly. Aliasing does two things. One frequency manifested as another. 2. Increasing actual frequency leads to decreasing apparent frequency. So, in fact, just to emphasize, let me put back before you and stress this point. As you increase the frequency from 0 to pi by 2 here, the frequency appears to decrease from pi to pi by 2 there. Now, the first thing we have to do if we want perfect reconstruction is to do away with aliasing. So, we put down a condition for aliasing cancellation. If we want y z to reconstruct x z, we must first do away with aliasing. And how can we possibly do away with aliasing? That essentially means we want tau 1 z to be equal to 0, or in other words, we want g 0 z h 0 minus z plus g 1 z h 1 minus z equal to 0. And in fact, if we wish to explicitly express the synthesis filters in terms of the analysis filters, we could do that as well. Let us rearrange this equation to get g 1 z by g 0 z is minus h 0 minus z by h 1 minus z. And of course, a very simple choice is g 1 z equal to the numerator, let us say plus or minus h 0 minus z, and correspondingly g 0 z is minus respectively plus h 1 minus z. This is a very simple choice of synthesis filters from the analysis filters, which can give us alias cancellation. Now, in fact, we can even spend a minute in interpreting what we have just said here in this very simple choice. I must of course emphasize, this is a simple choice, but definitely not the only choice. In general, you should note that there would be a factor cancelled in the numerator and denominator. So, more general choice would be as follows. G 1 z is of the form plus minus some factor, let us say r of z times h 0 minus z, and g 0 z is respectively minus or plus r z h 1 minus z. So, r z is in some sense the factor cancelled. When you divide g 0 z by g 1 z, some factor has been cancelled and what is left is h 0 and h 1. That is the way you should look at it. That is the more general situation. Anyway, Now, let us interpret what we had written here, namely G 1 z, this is a very simple choice of G 1 is h 0 of minus z and G 0 is plus or minus, you just interchange plus or minus here, h 1 of minus z. So, let us take the upper one, G 1 z is h 0 minus z, the other one follows similarly. You see, ideally, this is what the frequency response of h 0 should be. It should be an ideal low pass filter with a cutoff of pi by 2. So, this is what the frequency response should look like. This is 1. The height here. So, what would h 0 e raised to the power omega j omega plus minus pi look like? Or in other words, what is h 0 of minus z then? H 0 minus z with z replaced by e raised to the power j omega is essentially, of course, as you know, h 0 e raised to the power j omega plus minus pi. And that, as you can very easily infer, looks like this. Again, let us use the strategy of zooming and then contracting back again. So, I have pi minus pi there, 2 pi, 3 pi and so on. This is what h 0 look like, taking note of the periodicity, remember. This is minus pi by 2 there, this is pi by 2, this would therefore be 3 pi by 2 and so on. So, the zoomed h 0 e raised to the power j omega plus minus pi would look like this. It would have an appearance like this. And so on here. These pass bands, so to speak, are now going to lie at the odd multiples of pi, and you can continue that drawing. Now, once again we confine to the principal interval. So, the principal interval is here. And when we do so and then zoom back to emphasize only the principal interval, what do we get? We get this. Lo and behold, from a low pass filter with a cutoff of pi by 2, we have a high pass ideal filter, of course, again with a cutoff of pi by 2. So, this falls into place very well. In fact, the equation G1z is H0 minus z makes a lot of sense. All that we are saying is that on the synthesis side, if you had an ideal low pass filter with a cutoff of pi by 2 at H0, you should put an ideal high pass filter with cutoff pi by 2 at the point G1. And you know, if you look back at the other one of the two, namely G0, you would make a similar inference. G0z is H1 of minus z with a minus sign. So, if you look at the magnitude sense, again a high pass filter would become a low pass filter. In fact, I leave this to you as an exercise. So, exercise shows similarly that an ideal high pass filter HPF with a cutoff pi by 2 on replacing z by minus z becomes an ideal low pass filter with a cutoff of pi by 2. And that also makes a lot of sense for the other of the two requirements for alias cancellation. So, today we have looked at the condition for alias cancellation and we have interpreted the simplest of the conditions. Now, if you do not stick to the simple condition and if you have the factor of R z, all that we need to do is to say that we are also modifying that filter a little beyond just this low pass to high pass and high pass to low pass conversion. That R z factor would carry out that modification. So, we have taken one out of two steps today in building a perfect reconstruction 2-band filter bank. We have taken the step of alias cancellation. In the next lecture, we shall take the second step, namely perfect reconstruction. So, we have done away with tau z, I mean tau 1 z, but now we need to see what to do with tau 0 z, which we shall do in the next lecture. Thank you.